So today I want to talk about ammonia measurements from satellite and the new opportunities and discoveries that we've done for using this relatively new measurement of ammonia and its importance in aerosol precursors and nitrogen deposition. So ammonia largely comes from agricultural emissions. Most of it comes from livestock waste or fertilizer application. But the importance of ammonia is that ammonia then turns into particulate matter. And here shows the molar composition. I just picked Boulder, Colorado, because we'll be talking about Colorado today. But although ammonium by mass is relatively small, it's only mass 18 compared to organic sulfate and nitrate, but the chemistry happens by molar composition. And you can see that ammonia is the dominant cation and dominant base for atmospheric aerosol that neutralizes it. So once you make these ammoniated aerosols, they can then go on and dry deposit and wet deposition of nitrogen, for example, in federal class 1 areas such as national parks, where we see exceedances of nitrogen deposition above and beyond ecosystems. It can also then create particles which have implications for human health through PM 2.5 formation. And what's shown here is a study of particularly corn production and the role of ammonia used as a fertilizer and how that relates to PM 2.5. And basically that ammonia is one of the dominating factors in mortality morbidity in the central US due to these fertilization applications. So ammonia is really important, but we have these very large area sources that are somewhat episodic. For example, fertilizer application. It's not like a well pad. It's not like a vehicle exhaust where we're trying to understand emissions. So here are the satellite measurements of ammonia. There's YASI with on the satellite METOP A, B, and now C. There's the CRIS instrument, and I'll largely be talking about these today, mainly the YASI instrument. And you can see the pixel sizes are roughly 10 to 20 kilometers, of course, depending on whether it's nadar or at an angle. And YASI gives a column, CRIS actually gives a profile, and then there's slight differences in terms of the sensitivity, the density of the pixels. But overall, YASI and CRIS are the two most commonly used ammonia measurements. AIRS has also measured ammonia. It's not accessible to the public right now, and TESS is no longer operational or does special operations. And this was kind of the pioneering ammonia measurement was from TESS. So largely today I'll be talking about YASI and to a lesser extent CRIS. So despite ammonia being used particularly from YASI since the first published studies in 2008, there's been relatively little validation that's been done. So what's shown here is the first part of our HACAS project was really to understand how accurate are satellite ammonia measurements. So we used the NASA Discover AQ field campaign where for the first time we had, or among the first times, we had really good ammonia measurements on board. And then we had a suite of ground-based measurements as well and mobile laboratories. So shown in white here is a pixel. Here's the centroid of the pixel. And in this example, we had lots of different, we had aircraft, we had mobile labs, we had the C-130, the P-3. And then we can use that to reconstruct a column as shown in this panel. And here's the mixed layer height. We're in Colorado, so the ground is at a higher elevation. And then the airplane only went up to 4 to 5 kilometers above sea level. So we did have to do some assumptions on what the ammonia column was above and beyond that. But in general, this is a paper that's submitted to JGRA. What we can see is that if we look at the YASI column versus what we derive from the in-situ column with logical assumptions of what the profile should be above aircraft, we can see slopes that encompass 1. We see a intercept that's basically effectively 0, 1 times 10 to the 15 molecules per cubic centimeter is effectively a very, very low column amount of ammonia with reasonably good correlation. So with YASI, we see no significant biases. That implies that we can average over space and time. And the slopes are near unity, so at least for Colorado, it looks reasonably accurate. But the one thing that we did describe in this paper is you really need to pay attention to the spatial temporal windows. So in this case, with the mean wind speed 15 kilometers, which is about the size of the YASI pixel, corresponds to about plus or minus 1 hour in terms of transport time. So now that we know we can signal average satellites with Kong Soon at the University at Buffalo, we developed a oversampling algorithm that has been used for many other satellites, particularly NO2 and SO2. And we looked at, can we trade off, the single day of tracks versus a lot of overlapping tracks? And by using the spatial response function, can we get a higher, spatial resolution if we give up some temporal resolution? So when we do this, if we do it on a monthly average, we can get resolution down to about 2 kilometers. So here's the spatial pattern of ammonia on an annual average from Yazzie over the United States. And you can see in Western valleys, the Snake River Valley, the South Platte River Valley, San Joaquin Valley. And then over the Central Plains and Midwest, you see large amounts of ammonia, but you also see hotspots down in the poultry and not poultry, but the hog and swine areas of North Carolina, the poultry areas of Delaware and the Delmarva Peninsula, and Lancaster County dairy in the eastern US. So ammonia is everywhere, but it tends to focus where agricultural activities are dominating. So with that information, we can also look at, here's the same map that I showed before. Where do we have ammonia monitoring networks? Like I said, ammonia is a very difficult species to measure both in situ. And over the past decade, there's an ammonia monitoring network that's been put together. And we can see the hotspots. And with the satellite data, we can look at the 95th percentile, for example, of hotspots. And those are outlined in this white area. So you can see the South Platte River Valley, Snake River, San Joaquin, the Central Plains, but also other spots. But what you notice here is in these crosses and diamonds are where the ammonia monitoring network is. And at least for trying to understand emissions of ammonia, most of these AMON sites are not located near where the hotspots are. Now, that is perfectly fine if you're trying to look at downstream effects such as deposition. But if we're trying to invert the AMON network backwards, we need to be careful because these hotspots are really tiny and very narrow. Ammonia has a short lifetime. So the satellite can also be a guide to how we can interpret the ground-based network. And again, the length scale of these hotspots, at least for this percentile, is about 20 kilometers. And of the 14 top hotspots, only 5 have an AMON site within 100 kilometers. And of those, 2 of them only have long-term data and are at a relatively same elevation. For example, Rocky Mountain National Park is not representative of the South Platte River Valley. So if we compare the Yazzie oversampled annual ammonia map compared to the AM3 massage of NOAA GFDL, or the CMAC NEI, which uses the NEI emission inventory, you can see the general trends are okay. San Joaquin Valley, Central Plains, but the relative amounts of the columns, so these are all columns here, are significantly different. Yazzie has many of the hotspots. Massage is much more dispersed, doesn't show the hotspots as well. And you can see significant differences, for example, between the massage inventory used in AM3 versus the NEI and CMAC. So the general patterns are well represented, but the relative magnitude, say, between the San Joaquin Valley and the Central Plains are much different, and we can use satellite to help improve this. So focusing on Colorado, so here's a map of Colorado showing, capacity for feedlots. So this would be the Denver area here. This is Rocky Mountain National Park. And when we overlay the oversampling map, so again, here's the feedlot, here's the oversampling, and then this white line shows the 95th percentile. And you can barely see on the transparent, this hotspot region is right over where the feedlots. So we have really good confidence just based on our intuition of where ammonia is coming from, that the satellite is actually picking out these sub-regional aspects. So, we use the satellite data combined with in situ measurements from both the Discovery AQ, where there are aircraft flying around, as well as some of our own groups, eddy covariance flex measurements in Rocky Mountain National Park. And what satellite can do is, there was a question of where's the dry deposition of ammonia coming from? And the agricultural interests were saying, well, it's coming from the Denver metro area. And a lot of people suggested that it's coming from the agricultural regions. Well, we actually made flex measurements. And, the Discover AQ field campaign could show how the ammonia was being transported upward. We saw this with the mobile lab. But what we did is we looked for cases where we saw positive flux or cases where we saw positive flux, meaning emissions, or negative flux deposition. And what we saw is when the back trajectories went through this ammonia hotspot region defined by the satellite, we saw net deposition at Rocky Mountain National Park. When the back trajectories at Rocky Mountain National Park went through any other region besides this hotspot region, we basically saw no deposition or emission at all. So the satellite data is really helpful to kind of fingerprint that, okay, when we see deposition, that wind is coming from these hotspot regions. So this is one example of how satellite can be used and coupled to the in situ measurements. And then related to this, there are 26 national parks that are located within 200 kilometers of a hotspot or a 95th percentile of Yazi. So these hotspot centroids here are given by Martin van Dam of the Yazi from a paper that they published about a year and a half ago. But then the white lines and the other ones are the 95th percentile of just the column amount. So we know, at these levels, they typically scale pretty closely to the emission source or the locations of the emission sources, because if there weren't emissions, it would drop quickly below this 95th percentile. And you can see that even, cases such as like Yellowstone National Park, it's greater than 200 kilometers, but many of the federal class 1 areas, national parks, are located within 100 kilometers of a hotspot. And even in this case with Yellowstone, you can see, although the hotspot is defined in the lower part, southern part of the Snake River Valley, you can see the hotspot extending all the way up to the Tetons in Yellowstone National Park. So this is an example of how satellite can be used for not just understanding deposition, like with the study that we showed, but also, where should we be placing the next set of monitoring network? So those are averages, but ammonia also changes by month. And here's a map showing the monthly average ammonia and how the ammonia patterns change. You can see that basically agriculture is breathing. In the months of April, May, and June, you see a huge, so this is March, April, May, June, you see this huge bloom of ammonia, but it shifts over time. So we took that and we compared it and did a clustering analysis with the Yazi, and we also did this with Chris with similar results. So in these blue areas, you see typically a May peak and a gradual decrease over time. And this is consistent with the AMON network as well. Now, if we look at the AM3 emission inventories, you see, according to the colors here, you can see, but there are some differences, but the AM3 just does a double peak, and it just, the relative magnitude of that double peak changes depending upon the parts of the country. So we can look at the Western US, and unlike that broad peak in April and May, you instead see in the northern part a kind of peak later in August, and in the southwestern part of the US, more of a June, July peak. And this is, again, broadly consistent with the AMON sites in this region with more of a late summer, mid to late summer peak. And again, this is much different than what's being currently parameterized in the models. So the satellite, and the reason for this later peak in these regions is because these are largely driven by temperature-driven volatilization aspects of ammonia, whereas previously over the Midwest and central US, this is largely related to fertilizer application, which are typically done at the start of the growing season in April and May. So here's how satellites can be used. Here's a more recent study looking at the area of North Dakota where winter wheat is. And this is a time series starting in late April into May. And you can see, I'll go through it again. So here's May 1, and you can see the fertilization bloom, the red colors, on a couple days there throughout this entire region. And this is single pixel daily measurements of ammonia. And this just shows some new opportunities. During this time, we also saw, there aren't many stations, but there was one station that saw a significant increase in PM 2.5 over this case. So overall, satellites are accurate, bias-free, and sensitive to moderate to high column amounts. We need more validation, particularly in valleys where there's low thermal contrast for mid-infrared sounders. Generally, Yazi and Chris agree well over hotspot regions. I didn't show that, but that's a generally true statement, so they can be used to invert emission inventories. And really, satellites provide new constraints and opportunities for ground-based monitoring networks, like where we place them, for constraining emission inventories, both spatially and temporally, and looking at activities such as fertilization, constraining agricultural practices. There are no databases for that. With the pixel scale measurements of satellite, we can see these. And of course, using ammonia measurements from satellite as an aerosol precursor to look at PM 2.5 formation. So I thank NASA HACAS for this opportunity to work on this. And if you have any questions, my name is at the start of this. And I thank you for your attention.